Okay. Okay, so in this segment we are going to discuss about uh, the mode shapes in a particular finite string, because we started that discussion but we never in the previous segment we started it, but we never completed that. So in this segment what we will do is we will complete the concepts of mode shapes, normal modes on a finite string. And for that I'll just write this thing back, that what we had, where did we stop last class? We said that okay, say y xt is say some c plus e raised to say I in form of kx I am writing omega t, then plus say c minus I kx plus omega t, right. So this we wrote as the solution of our partial, I mean the wave equation, this. Right. And this we did with a background saying that we are trying to talk about modes. So the definition of mode is that every particle will be in sync, and that is why this omega will be same for all. So then we set the assumption that y of xt will be some y of x times e raised to minus I omega t, and so that's how we got the differential equation. Partial became a ordinary differential equation. We solved that to get it. So that's how we did it. But then you have to keep it in mind that again whatever we did, that was for an infinite string. Nowhere we mentioned that there is a boundary condition in this. We just solve this equation in a way with a view that if harmonic motions are happening, so this is that part. So the only change is this, from the infinite string discussion which we had earlier. From that, this discussion is differing only in this assumption, if you right. So that you should always keep in mind, because we discussed earlier also an infinite string, now also we are discussing an infinite string only. But what is the difference? The difference is that we are saying that everything, all the particles are moving harmonically. Now so there is another way to see this, not by writing it in this way and solving it. There is another physical way to interpret that also. See, this equation is telling you that on an infinite string, whatever may be the shape of the time dependence of y, that only will be the shape of the space dependence of the same y, because there is only a constant factor between the shapes of time and shapes of displacement. That means if harmonically you oscillate something in time, in space also it will be harmonic. So that a statement you can make just by looking at this. Okay. And if you do that, you can just say, for example, any of this thing is just a wave which will move in an infinite string, and at the same time the others from other side also you can start a wave, and that will be the what do I call the equation for that. So the combination of both of them will be this. But then here again in this kind of argument, you are again saying that you have sent the same harmonic signal from both sides. Okay, so in this side, from So this is going to right, and this is coming to left. Now both these waves you have chosen that the same kind of harmonic frequency you will apply, and then this is how the wave field is on the string. Okay. Now what happens if I want to write it's just for completeness. So this is the complex form. I'll just write the real form also so that we can use it. So this C plus you can write as say a plus e raised to plus I phi plus, and C minus you can write say a minus e raised to plus I phi minus. You can always do that, and once you do that you can always split them into real parts. So a plus cosine of what will you get, kx minus omega t plus phi plus plus a minus cosine of kx minus omega t plus phi minus, right. So this directly you can write the real part. Again just emphasizing that writing in exponent form directly helps you in doing this. If you don't do that, it's a bit algebraically complex to do this. Okay, anyways. So this is what is your wave. So this actual physical wave. But then now think that in terms of energy. Now this wave is taking some energy right way, right, towards right side, whose magnitude is proportional to the amplitude square. Okay, and at the same time some wave is coming from left side whose energy is proportional to a minus square. Okay, so that means depending on the size of a plus and a minus, either energy will be transferred to right side or to left side. But what if we have the condition that a plus is equal to a minus? Because up to this point when energy was transferred in either of the ways, these are called the travelling waves. Okay, even when both are there. Anyway, when a single wave is present, it's very easy to say that okay, wave is travelling. But when both are there, still it will be called a travelling wave, because if these parameters a plus a minus are different, then some energy will be transferred in some direction. Then still it will be called a travelling wave. Fine. But now what happens if this condition is satisfied? A plus becomes a minus. Now, so just do the algebra here. So these two terms, you can take the a common, and then what you can have is your y of xt will become a times so cos a plus cos b, you express that in terms of a product form. Okay, and you will get, I'll just write it down, which you will get like this, the 2a cosine of kx, then plus phi plus minus phi minus over 2 times cosine of omega t minus phi plus phi minus over 2. Okay, so this is what you will get. Now what do you observe from this? The most important fact which you want to talk about. Compare with this. Now here, whatever manipulation you do, you can never split the x and t as two different functions, which now you have been able to do, right? In differential equation language, the separation of variable thing, you know, so that sort of thing in two functions, which is completely, one function is a function of x, the other one is in time. So that you could do now. Fine. Now, what does that mean physically? It means that whatever this shape is, this first part, which is a dependent on space, okay, space dependent function, whatever this is, it is just getting multiplied with a time dependent sinusoid, right? That means you will have whatever this shape is, it just standing there, it gets diminished, it gets enlarged, but it stands there, it doesn't move. Okay, so that's what is the meaning of you have now got a standing wave pattern. Okay. So now that means the energy is not anymore getting transferred. At the same location, the energy is either getting converted from kinetic to potential, potential to kinetic, but no energy gets transferred across the space displacement. Okay, and that is where you see the picture. Always, you might have seen this picture, no? That wherever standing wave concepts are discussed, you would see a picture like this. Not only that, you will see even this. Right? You will see a picture like this. What does this picture tell you about this equation? So, in fact, here we are not even having a wall like that. You can think that, okay, this wall is continuing this side also and this side also, but this pattern is everywhere. There is no wall as such. Okay? But whatever these points are in space, once they are frozen, they are frozen. They are not moving. Okay? But then this picture, you should never see that as a whole like this. Whenever you see this, you have to visualize this as a moving picture, saying that, okay, it starts with, say, this shape. Okay, then this factor, so now this is this, the space dependence, and now this thing is taking over. It is shrinking it, and it is shrinking in even negative direction because cos will go to negative. Okay, so after some time it will come to this shape. Then after some time it will come to this shape. Then after some time you will go to this shape, and like that, because cos has now become negative. So the same shape is now oscillating at the same location, and that's what I was talking about, energy, because see, these points are anyway fixed, so there is no way that energy can move across those points. Those are completely like rigid blocks, fixed rigid blocks, so energy cannot move. So whatever happens is Now when this is in completely in the zero displacement condition, everything is in terms of kinetic energy form, and whenever it is in the maximum deflected form, everything is in terms of potential energy form. So energy only gets converted from kinetic to potential in every such loops, if you consider each of them, and then you know these words, right? So these are the nodes and these points are the antinodes, right? So that means between two nodes the energy just gets converted from one form to the other, but it never gets transferred. But so this is a very theoretical thing. Practically, or even in this case, even in theoretical case, you know what happens when you start the wave to propagate on this string, both these equal amplitude waves. From the beginning, this kind of a thing cannot happen. It will take some time. During that transient period, the energy will flow and will fill in all these buckets, sort of, during that time when the transient is still existing. Then once the steady state has reached, after that these points will be completely frozen and you don't have to transfer any energy then. Whatever is going from that side and this side, they balance, and no energy. So whatever energy is there, it is just sitting inside this. It is theoretical. But in real life what happens is there will always be some friction or damping part. So in those cases these points will not exactly be zero, there will be slight deflection there. So those slight deflection will allow you to transfer the energies from loop to loop, and some small amount of energy will be transferred. Okay. So that's the meaning of the standing wave. And again, you should never think that standing waves are possible only when you put restrictions on the boundary. Here we are still considering the infinite string. We have never discussed about boundaries, but still we are having the condition of standing wave where no energy is going. So that's the condition of, so the only requirement for that was this, that the wave that is going to left and the right, they must have the same amplitude, no other condition. They could be having different phases, there is no issue. So this phi plus and this phi minus, they never had any issue. Okay. So only thing is that, because that will come into picture here, those phases, and it doesn't matter. It will just change the shape in a way, shifted version, and that shifted version will be oscillating with a particular phase. So that's it. So that was about the standing wave versus travelling wave, and now we are in a position, because we have this form, we can now talk about the waves and the modes in finite strings. Okay, so we'll stop here for this segment and we will continue in the next segment.